Welcome to this web lecture dealing with electromagnetic waves and antennas. It is part of the master course Microwave Engineering. In this web lecture I will talk about wireless power transfer. I will start with an introduction, then I'll go briefly through the history. That brings me to the principles and limitations of the technology, and in the end I will discuss a few designs. Let's start with the introduction. Wireless power transfer is a special case of energy harvesting. Energy harvesting used to be known as energy scavenging, and it is the process where you take energy out of your environment to power electronic devices. What are the most common sources for energy harvesting? Well, we have motion, movement. The dynamo is well known, and shown in this example is a so-called dyno torch. Pressure can be used. What is shown here is a switch made by an ocean working with piezoelectricity. When you push the button once, that gives enough energy to transmit a few bits to a receiver connected to a light fixture that can switch on or off the lights. Temperature differences can be used to harvest energy using the Seebeck effect. It is a technique used in satellites, and in satellites the temperature difference is generated most of the times by a thermonuclear generator. And finally, maybe the most well-known technology for converting energy from the environment into electricity is by solar cells. What is missing here is the use of radio waves. The reason is that it is a fairly new technology and there are not a lot of commercial products yet. Where do we want to use it? We want to use it to replace batteries or to charge batteries of small autonomous wireless sensors. And where do we want to use these sensors? In a so-called smart house. We envisage a house connected with hundreds, maybe thousands of sensors, and these sensors measure locally temperature, light, humidity, CO2 levels, presence of people, and so on. And all these sensors need to be powered. We can't power them from the grid because the cabling is too expensive. Using batteries is also not feasible. If you have that many sensors, you have a day job in finding out which sensors are down and in replacing the batteries. And in replacing the batteries, you also get an enormous ecological problem. So we need alternative power sources. We have mentioned a few, and then the next question, of course, is how much power can we obtain from our environment? Well, let's look at the power densities. And what we'll see from this table is that we may expect the most power from light. But if we are inside a house, we cannot guarantee that we will always have light. Maybe you want to charge some equipment overnight and then the lights will be off. There will also be rooms where there is little or no light. So light is not an option. Vibration, well, not in a house. Temperature differences in general will be very low, so that's also not an option. So then what remains is radio waves. Can we get enough energy from what's in the air? If we look around us, the strongest signal comes from GSM. And if we look at the power densities, we see that the power density is very, very low. So this is not really a good option. What we want is wireless power transfer. It's not harvesting because we bring in our own transmitter. If we look at wireless power transfer, we have two flavors. This flavor, charging inductively, is not what I'm going to talk about. And the reason is that this is for short distance, for near contact. And from a user point of view, it's not even wireless. Look, there's a wire. Actually, it's not wireless, it's plugless. What I want to talk about is using radio waves. So we have the system here, we have a transmitter, and then on a distance, that's important, we have the receiver. The receiver in its most basic form consists of an antenna connected to a rectifier. The DC voltage coming out of the rectifier is used to power our application. The combination of antenna and rectifier we normally call rectenna, from rectifying antenna. When did this start? I think that the first experiment on wireless power transfer was performed in 1931 at the Westinghouse laboratories in the USA by a man shown here in the middle, Harold von Nobel. What he did was he used a half-wave transmit dipole antenna over here, used at hundreds of megahertz. Then he had a half-wave dipole antenna for receiving, and that was directly connected to a light bulb, which you see glowing here. Why did it work? Well, mainly because he used 15 kilowatts of power, which is a lot, and which is very unhealthy. We know now that at these distances and this power and this frequency, the body temperature will heat up with 1 degree every minute. Still, I think that the experiments have been very short because I know this man lived to be 76. I don't know about the women. After this experiment, the interest turned down a bit. The reason being that it was not possible to generate high amounts of power at higher frequencies where your antennas could be smaller. We had to wait for that till after the war. And then in the 1960s, new experiments were conducted at Raytheon. William Brown was capable of flying a model helicopter powered by radio waves. He used 5 kilowatts at 2.45 gigahertz using the magnetron being invented in the war. He was able to collect 270 watts of DC power at the helicopter, and that helicopter flew at a height of 9 meters. This project at Raytheon lasted till half the 80s, and then again interest became less. Interest started again around 2000. The reason being, I think, the success of RFID, radio frequency identification, which is closely related to the subject of WPT. Also at Holst Center IMEC and Eindhoven University, we have been working on this for nearly 10 years now, and we have come a long way. We started in 2007 in our first demo, where we used 8 rectifying antennas, to power a wall clock at a distance of 1 meter. Nearly 10 years later, we can do the same with having only 1 loop antenna, 1 diode, because we better understand the physics behind WPT. Which brings me to the principles and limitations. If we have a transmitter, we know that the waves will propagate spherically, depicted here. This means that for every doubling of the distance, my power density will decrease with a factor of 4. You can compare it with blowing a balloon. The amount of rubber will stay the same, but the more air you blow into the balloon, the rubber will be displaced over a larger distance. So if you put an antenna at a larger distance, there's only a small amount of power you can collect. How much? Well, if we look at the strongest signal in our environment, which comes from GSM, we may expect on the average 0.1 microwatt per square centimeters. It's not much. If we bring in our own transmitter, as we do in WPT, we can at least increase that with a factor of 4. It's still a low amount, but we can do something with it. We cannot use it to charge our phone, not in this way of WPT, but we can use it to power duty-cycled sensors, as I will show later on. That brings me to the design. The biggest problem in designing a rectifying antenna, is to create a sufficient voltage. Our electronics needs a voltage of at least 1 volt, preferably 1.5 volts, to operate. And if we look at an antenna, small antenna connected to a diode, in general we don't get that amount of voltage. If we're looking at this part of the system, what we need to do is first of all make sure that all the power that gets into the antenna also gets into the diode. We need to be very, very careful about the matching, which is not a trivial task, but we know now how to do it. And then you get an output voltage in the range of 0.1, 0.2, maybe 0.3 volts. And what we need then is a DC-DC boost converter to bring this up to a voltage of 1 volt or even higher. And then we store it in a battery or a capacitor, and use that to power our application. I'll show you an example here. What we see here on the left is a transmitter, and on the right our rectenna. We have an antenna, a rectifier, we have a boost converter, and what we see here is that it continuously powers a thermometer that is connected to a liquid crystal display. Let's have a closer look at this so-called rectenna. What we see at the bottom is the electronics. That's the boost converter and all the components associated with it. On the top we see the antenna. The antenna is not a standard antenna, it has been specially designed to make it small. It's only a tenth of a wavelength, which is very small, and it is directly connected to the rectifier because we know how to calculate the impedance of the rectifier. And therefore we have been able to make this relatively small rectenna. This one measures 6 by 10 centimeters at a frequency of 915 megahertz, which is the smallest in the world at this frequency. In the example I have shown how we continuously power a thermometer. In real life we will not use a continuous powering, but we will a duty cycled operation. If we look at the temperature, normally we don't want to know the temperature continuously, but once every couple of minutes will be sufficient. And that means that we can temporarily generate much more power. So we will only take the power when we need it and collect energy in the time in between. So for the rectenna shown, we know that we can collect 30 microwatts DC continuously at a distance of 10 meters, provided we have a 3-watt source. But duty cycled, we can, for example, collect 60 milliwatts of DC power for 40 milliseconds every 2 minutes at the same distance. And this amount of power and the time is sufficient to wake up a radio, to perform a measurement, transmit the measurement results, do some handshaking to be sure that the data gets over, turn off the radio and start collecting energy again to do the same trick 2 minutes later. If we look at the antenna, we still think it's quite big, and there's another problem associated with this antenna. The antenna will only operate when it is freestanding. We cannot place it on metal. To overcome this, the size and not being able to put the antenna on metal, we made a new design, shown on the right. The first thing we did was compress the electronics, as shown here. Then we moved to a higher frequency from 915 megahertz to 2.45 gigahertz. And then we redesigned the antenna. We made an antenna with a metal ground plane. This rectenna can be placed on any surface you want, metal or non-metal. It will keep going. And you see it going here with the same thermometer. Which brings me to the conclusion of this talk. We know that radiative wireless power transfer is an emerging technology. If you want to get most out of your WPT, and we do because we are dealing with very low power levels, we need to know exactly how the semiconductor rectifier works, and we need to know how the antenna works. To be able to design new antennas, of which I have shown 2 examples, we need to understand the basics of antennas. And to understand the basics of antennas, you need to follow this course on microwave engineering. I thank you for your attention, and I hope to see you at the next web lecture.